Lyapunov equation is the same equation regardless whether we write it in continuous or in discrete form. Discrete form is basically taking finite steps but then having to compute effective noise around each step, accumulated noise. One thing we have learned is that in nonlinear dynamics, noise always has memory. So no matter how we go, we cannot pretend we have just uniform Gaussian noise. It's always remembering where it came from and how the nonlinear flow deformed it. Now, the next step is a little bit technical, but very beautiful. So we'll take Lyapunov equation, its solution, and we'll bring it into resolvent form. Which will enable us to do some magic in a complex plane, which is kind of a pleasant surprise. So, we have Q, which for a system which is contracting can be written at a fixed point of such a system as the noise, which is valued the fixed point, so it doesn't change with time, T times A transpose T times A. And we can do following trick. We have these two integrals, but maybe we could get rid of these integrals. We'll learn in, or maybe you remember from other nonlinear dynamics, there are very smart ways of getting these things into denominators and study poles of integrals. So what we'll do is we will use Dirac delta function for plus to minus infinity line and write it in this representation, which I hope you remember. That's representation that you always use in Fourier analysis for infinite integrals on a line. And we can insert it in here by adding one integration in time. So we can write this at 0 to infinity dt dt prime. And then we can replace this delta Dirac function by its representation, Fourier representation, omega e to the I omega t from here, but then we also have plus ta from there, delta. Then on the other side we have minus I omega t plus t transpose. And remember, if this was rotation group, A and A transpose would be inverses of each other, but this is just some general non-normal matrix, non-diagonal algebra, etc. So they don't have such a simple relationship. But now what we can do is we can actually do this both integrals as long as A, well, let's just do them formally and worry about it. So there is also 1 over this 2 pi. So I can write it as 1 over 2 pi from here. And we can write it as minus infinity from there to infinity of d omega, the variable dual to time or frequency, I omega minus A delta 1 minus I omega minus A transpose. And it's this resolvent form that will enable us to disentangle, even though our original arguments are all constructed for either fully contracting flow, in which case we go forward in time, or for fully expanding flow, in which case we go in the adjoint direction. We go from the past to now. So those two separate cases were okay, but this resolvent form will enable us to handle also hyperbolic case, combine both contraction and expansion.